When you have a twice differentiable function of a single variable, a critical point occurs where the first derivative is 0. In this case, the second derivative test tells you that if the second derivative at that point is positive, then the point is a relative minimum. If the second derivative is negative, then the point is a relative maximum. And if the second derivative is 0, then the test is indeterminate. In other words, you cannot conclude whether you have a relative minimum, maximum, or an inflection point. Now let's consider a twice differentiable function of two variables, f of x and y, with continuous second partial derivatives. We denote the partial derivatives like this. By the way, the second partials of f with respect to x and then y, and with respect to y and then x, are equal because we are assuming that all partials are continuous. A point determined by x0, y0 is a critical point if both first partials are 0. To use the second derivative test to determine the nature of that critical point is not as obvious as in the case of a function of a single variable, so first we will look at some key examples. Perhaps the easiest non-trivial example in the single variable case is the parabola x squared. Since the derivative at 0 is 0, and the second derivative is equal to 2 at any point, it has a minimum when x equals 0. In the case of two variables, the function x squared plus y squared gives us a paraboloid with a minimum at the origin. If we consider cylindrical coordinates, we can write z equals r squared. Cylindrical coordinates are just like polar coordinates in the xy plane. Now, if we look at cross-sections in various planes where theta is constant, then we can think of two-dimensional curves in the RZ plane represented by that equation. Since the equation in the RZ plane is z equals r squared, we can apply our single variable derivative test to determine that r equals 0 gives a minimum of z in that plane. That is, the derivative of z with respect to r is 2r, and the second derivative is 2. So when r is 0, the first derivative is 0 and the second derivative is positive. Furthermore, this is true for all values of theta. Now suppose we modify our quadratic function to x squared plus y squared minus 4xy. As with our previous example, the traces in the xz and the yz planes are the parabolas z equals x squared and z equals y squared. However, the trace in the plane y equals x opens downward. To understand what is happening, we can again think of the graph in terms of cylindrical coordinates. In this case, it is z equals r squared minus 4r squared cos theta sine theta, and that simplifies to z equals r squared times the quantity 1 minus 2 sine 2 theta, because the sine of 2 theta is 2 cosine theta sine theta. We can then view cross-sections in different planes by choosing values of theta from 0 to 180 degrees. Here's what this solid looks like. For a given value of theta, we can look at the derivative of z. The derivative of z with respect to r is 2r times 1 minus 2 sine 2 theta. Remember, the theta is a constant there. And the second derivative is 2 times the quantity 1 minus 2 sine 2 theta. When r is 0, the first derivative is 0, but the second derivative depends on theta. In other words, the second derivative of z is sometimes positive, which gives a minimum as on the blue curve, and sometimes negative, giving a maximum as on the red curve. Now let's consider a more general case, but we'll keep the critical point still at the origin. We would like to know what the cylindrical representation tells us about the partial derivatives with respect to x and y when theta is a fixed angle. Well, let's see. X is r cos theta and y is r sin theta. So the derivative of z with respect to r can be broken down into the derivative of z with respect to x times dx dr plus the derivative of z with respect to y times dy dr. And that gives us this. As for the second derivative with respect to r, we have to be careful. We take the derivative with respect to x times dr dx, and then the derivative with respect to y times dr dy. And the end result is this here. The relevant formulas for the first and second derivatives of z with respect to r are these. Remember that we are considering theta a constant. First, we notice that the derivative of z with respect to r is 0 when the derivative with respect to x and the derivative with respect to y are both 0, which tells us that in this case the origin is a critical point. Next, we consider the second derivative. If it is positive for some values of theta, but negative for other values, then the origin is a saddle point, as in the last example. But how can we tell in general if this happens, or if it is positive for all values of theta, or negative for all values of theta? Using the second partial derivatives with respect to x and y to determine whether the origin is a saddle point, a relative minimum, or a relative maximum, boils down to the question of whether the expression for the second derivative of z with respect to r changes sign for different values of theta or always has the same sign. To simplify the notation and focus on what is important, let's rewrite the second derivative like this, where a is the second partial of z with respect to x, b is the second partial of z with respect to x and y, and c is the second partial of z with respect to y. The question now is, what conditions on a, b, and c determine whether the second derivative with respect to r is positive or negative for all values of theta? To answer this question, we'll factor out the sine squared of theta, like this. If the sine of theta is 0, then this factoring is not correct, but in that case the second derivative is a, because the cosine of theta would then be 1 or negative 1, and we have cosine squared times a. In all other cases, the answer depends on that expression there. So let's consider that expression. So here we have the second derivative of z with respect to r. Let's let v be the expression in parentheses. Since theta is the variable under consideration, let's set u equal to the cotangent of theta so that we have v equals au squared plus 2bu plus c. Then it follows that the second derivative of z with respect to r is the sine squared of theta times v. If a, b, and c are such that v is always positive, then we know the critical point is a relative minimum provided a is also positive. This would mean the graph of v lies entirely above the u-axis. By the quadratic formula, the graph of v does not cross the u-axis if 2b squared minus 4ac is less than 0. Or in other words, b squared minus ac is less than 0. And by the way, when you apply the quadratic formula here, you have to realize that the middle term is 2bu, not bu. Likewise, if a, b, and c are such that v is always negative, then we know the critical point is a relative maximum, provided a is also negative. And this would mean the graph of v lies entirely below the u-axis. Once again, for this to happen, we would have to have b squared minus ac negative. On the other hand, the critical point is a saddle point if a, b, and c are such that the graph of v crosses the u-axis, because then v is sometimes positive and sometimes negative. And this would happen if b squared minus ac is positive. If sine of theta is 0, then we know from before that the second derivative of z with respect to r is a. In all other cases, the second derivative of z with respect to r is sine squared of theta times v. And since sine squared of theta would be positive, the sign of the second derivative depends on the sign of v. Thus we can state our second derivative test when the origin is a critical point as follows. If b squared minus ac is positive, then the origin gives a saddle point. If b squared minus ac is negative and a is positive, then it gives a relative minimum. And if b squared minus ac is negative and a is negative, then it gives a relative maximum. Recall that a is the second partial with respect to x at the origin, b is the second partial with respect to x and y at the origin, and c is the second partial with respect to y at the origin. What about cases where the critical point is something other than the origin, say x0, y0? If we translate our function so x0, y0 becomes the origin, then the translated function still has the same shape as the given function. In other words, if we let g of xy be f of x plus x0, y plus y0, then g at the origin is the same as f at x0, y0, and furthermore, all the partial derivatives of g at the origin are the same as the partial derivatives of f at x0, y0. Since our previous result applies to g at the origin, we can use these substitutions for a, b, and c to arrive at the second derivative test for the general case. If f of xy is twice differentiable in x and y with continuous partial derivatives, the first partials with respect to x and y at x0, y0 are both 0, in other words, x0, y0 locates a critical point, and a, b, and c are these second partials at x0, y0, then x0, y0 locates a saddle point of f if b squared minus ac is positive. It locates a relative minimum of f if b squared minus ac is negative and a is positive. And it locates a relative maximum of f if b squared minus ac is negative and a is negative. If b squared minus ac were to equal 0, we would not be able to conclude anything from the second derivative test.